Hello, my dear children, and welcome back. I know, exams are just around the corner. And so many of you have told me, sir, this thermodynamics chapter is so scary. It feels a bit heavy with all the new terms and formulas, doesn't it? It's so easy to feel a little lost.
And I get it. You look at the textbook and it feels like you're about to climb Mount Everest. That feeling, it's completely normal, so you are not alone. But you know what? We are going to make this mountain a tiny little hill. So just relax, take a deep breath. We're going to break this whole chapter down into small, bite-sized pieces. I promise you, by the end of this session, you'll be thinking, oh, was that all? Let's master this together.
Right, here's our game plan. First, we'll see what this big word thermodynamics even means. Then, we'll talk about system and surroundings. After that, we'll get into heat, work, and energy, tackle the most important first law, meet its close friend enthalpy, and then we'll give a quick revision for your exams. Ready? Chalo, let's start. So what on earth is thermodynamics? Well, in simple words, it's just the study of how energy changes. You know, like how the chemical energy in your LPG cylinder turns into heat to cook your Maggie? Yep, that's thermodynamics, right there in your kitchen.
The book definition is also quite simple, really. It's just about how heat, work, and energy are all best friends. Think of yourself as an energy detective. Your job is just to find out where the energy came from and where it's going. That's it. Now, to be a good energy detective, you need to know what you're looking at. In thermodynamics, we divide the whole universe into just two parts. And the best way to understand this is with something we all love, a nice hot cup of chai. So, this system is just whatever we are paying attention to. It could be the chai in your cup, or maybe a chemical reaction happening in a lab beaker. And the surroundings? Well, that's just everything else. The room, the air, the table, even you. Simple, right? It's just the system and the rest of the universe. Okay, now there are 3 types of systems. And trust me, understanding them is easier than watching one of those 30-second Instagram reels you all love so much. And we're going to figure it all out with our chai example. First, we have the open system. Imagine a hot cup of chai just sitting on the table. It gets cold after some time, right? That means it's losing heat to the room. That's an exchange of energy. And you can see the steam coming out. That's water vapor, which is matter. So an open system exchanges both energy and matter. Easy. Next up, a closed system. Think about a pressure cooker at home with the lid on tight. When you put it on the stove, it gets hot, so of course it's exchanging energy. But can the steam escape? No, so no matter is exchanged. A closed system exchanges energy, but not matter. And finally, we have the isolated system. Your thermos flask is a perfect example. It's built to keep your chai hot, so it tries to stop heat from escaping. And with the lid on, nothing can get in or out. So an isolated system is one that exchanges neither energy nor matter. Well, ideally. Now have a look at this. This is the exact diagram from your NCERT book. Open, closed, and isolated. You just understood all of it with a simple cup of chai. See? You already know this stuff. This chapter is not so tough after all. Okay, now that we know about systems, let's meet the 3 main characters who cause all the action. I like to call them the 3 musketeers of thermodynamics: heat, work, and internal energy. So let's break it down. Internal energy, which we call U, is basically the total energy hiding inside a system. Now, the only way to change this internal energy is to transfer energy in or out. And there are only 2 ways to do that, either as heat, which we call Q, or as work, which we call W. That's all. Now listen very carefully, bachcho. This part is super important for solving all the problems. It's the sign convention. The rule is simple. Think of the system as yourself. If something good comes to you, it's positive. So if heat is given to the system, Q is positive. If work is done on the system, W is positive. And if energy leaves the system, it's negative. Simple, na? All right, everyone, it's time for the hero of our story, the first law of thermodynamics. This is like the master rule of the entire universe for energy. It's so powerful, but believe me, it's also very simple. You've been hearing this since you were in middle school, right? The law of conservation of energy. Well, the first law of thermodynamics is just the grown-up mathematical way of saying the exact same thing. It's the universe's own accounting department. And here it is. Delta U equals Q plus W. This is the star equation of the chapter. You must remember it. It just means that the change in a system's internal energy, that's delta U, is exactly equal to the heat you give it, Q, plus the work you do in it. That's it. Every bit of energy is counted for. Nothing just appears or disappears.
Okay, let's try a typical exam question to see how this works. This will show you exactly how to use our STAR formula. Look at these three situations on the screen. Let's figure out what happens to the internal energy, delta U, in each one. Okay, let's do this step by step. For the first one, no heat means Q is 0. Work is done on the system, so W is positive. So delta U is equal to a positive W. Internal energy increases. For the second one, no work means W is 0. Heat is taken out, so Q is negative. Delta U is negative. Internal energy decreases. And for the last one, heat is supplied, so Q is positive. But work is done by the system, so W is negative. That means delta U is Q minus W. See, it's just simple logic with the formula and our sign rules.
Now, you might be thinking, sir, if we have internal energy U, why do we need this new thing called enthalpy, H? And that's a brilliant question. Think of enthalpy as the more practical, real-world cousin of internal energy.
Here's why it's so useful. Think about it. Most reactions in your chemistry lab, they happen in an open test tube or a beaker, right? In that situation, the pressure on the system is just the atmospheric pressure, and that stays pretty much constant. Well, it turns out that when you measure the heat change at a constant pressure, you're not measuring delta U. You're actually measuring something else, and we call that delta H, the change in enthalpy. It's just a more convenient measure for everyday experiments. Okay, the formal definition is H equals U plus PV. But for your exam, the most important thing to remember is this. The change in enthalpy, delta H, is simply the heat that is exchanged at constant pressure. Just remember, delta H is heat at constant pressure. This is a very important point.
You have all done a fantastic job. We've covered all the main ideas. Now, let's do a super fast revision of the things you absolutely, positively must know for your exams. These are the final takeaways. Ready? Rapid fire. System types. Open, closed, isolated. First law, delta U equals Q plus W. Sign conventions, what comes into the system is positive. Enthalpy, delta H, is just the heat change at constant pressure. And for gases, don't forget the relationship, delta H equals delta U plus delta NGRT. If you remember just these 5 points, you are in a very, very good shape for your exam.
And that's it. We did it. You have made it through the core of thermodynamics. See? When we break it down into simple parts, it's not so difficult at all, is it? I am so proud of you for getting through this.
And as we finish, I'll leave you with a little question to think about. Our body is a perfect open system, isn't it? We take in food and oxygen, we give out heat, we exchange both matter and energy. So my question is, what kind of work does our body do every single day? Think about it. Okay, my children, all the very best for your exams. Study well, stay calm, and you will do wonderfully.